So let's imagine for a minute that that radius is equal to 1. If that radius is equal to 1, then this sine value, if we consider this to be an xy coordinate system, that sine value is the y value of that coordinate. Let's say, for sake of argument, this point up here in space was the point, I'm going to go with 3/5, 4/5. It's got to be a little bit of a weird number because this circle is only radius 1. So I need a point that's on that circle of radius 1. And you can check that point is indeed on the circle of radius 1. So if we want to know this height is that 4/5. Fair? So our sine function, we are going to associate with that y value on our circle of radius 1. If we can find where our ray intersects a circle of radius 1, that y value is the sine function. Fair? Now, how does that compare to the opposite over hypotenuse? Well, you can certainly see I've got a little triangle here, right? That pink, blue, and part of that gray radius form a triangle, right? Well, its opposite side is that y value. The hypotenuse of that triangle is the radius of the circle, 1, so y over 1. Fair? So that does match our triangular definition. Okay, well, what if we wanted the tangent value? Now, we could find the tangent value in a couple of different ways. I want a nice bright color here. Those are not bright colors, those are terrible colors. There we go, bright color. We could find this tangent value in a couple of different ways. We could measure this, but this length, which I think we called H2, that length H2, what happened to my color? There we go. That height H2, well, I want to write that height in terms of this x and y. So if we consider this x value and that y value, we know that the ratio between the radius in ratio to that H2, that ratio should be equal to the ratio between x and y. Is that fair? Good old similar triangles. If we solve this for H2, well, don't solve for H2. Yeah, solve for H2. We'd get Ry equals H2x, or R times y equal over x equals H2. But what's our radius? The radius is equal to 1, right? So that's a 1. So y over x, that's our H2, but our H2 is supposed to be our tangent function. So yeah, we're used to thinking of our tangent function as opposite over adjacent. So we're used to thinking of it as the ratio between these sides. Well, how is it supposed to be this physical length then? Well, that physical length is equal to the ratio between the opposite and the adjacent, between the y and the x, because of similar triangles. So are we finding the ratio between y and x, or are we finding this physical length? We're finding both. Neat. Similarly, let me get this out of the way. This diagram is going to get messy. Similarly, if we want this secant length, that pink length, we could find the, physically find that pink length there, but I want it in terms of x and y. So we're going to do the same thing. We're going to set up similar triangles. So again, the ratio between the radius and y has to be equal to, don't want radius and y. I don't want radius and y. How about the difference, the ratio between the ratio between the radius and the x value. The ratio between that radius and the x value has to be the same as the one between the secant length and the radius of the circle. So this to that is the same as this to that. Fair? Now, you don't have to memorize all these constructions, obviously. Get rid of some of those lines so my diagram doesn't go crazy. But if you simplify that, notice it was, what was it, r over x equals the secant length over r. Is that right? Well, those r's are just ones because that's our radius of 1. So, gosh, our secant just turns into 1 over x. All right. 1 over x. So again, given that point, that 3, 5, and 4, 5, if all we know is that point, that intersection point there, let me get all the rest of this stuff out of the way. If all we know is that intersection point, lost my circle. If all we know is this intersection point at 3, 4, and 4, 5, well, we can find the sine value just by knowing that y coordinate. We can find our tangent value by finding our y value over our x value. That's going to be 4/3 when we simplify it. So this length there is 4/3. This length here is the 4/5.
No, wait a minute. You said it's 3/5 and 4/6. How is it 3/4 now?
Oh, multiply both by 5? Oops, sorry. That's supposed to be 3/5. Thank you. Is that better? Okay, thank you. I always say it is much easier to do mathematics with a bunch of people behind you who can go, dude, it's supposed to be a 5. It's very helpful. So if ever I do something like that, I always encourage you guys to shout at me. So the secant is 1 over x. So that's 1 over the 3/5, which is 5/3. So that pink length is 5/3. So all we need for those 3 trig functions is that 1 point. Questions about that so far? Oops. Now, hopefully you're wondering about the other three functions, right? We've got sine, tangent, and secant, which might be a little weird because we always say we focus on sine, cosine, and tangent. Where's cosine? And where's cosecant? And where's cotangent? Notice it's all the co-functions we haven't talked about yet, right? So what does the co in our co-functions refer to? When we talk about the co-functions, that co is for complement. So there are complementary functions. What did it mean to be a complementary angle?
Adds to 90 degrees.
Perfect. What makes that 90 degrees? Now, I said perfect because you're absolutely correct, but what makes a right angle, right? 90 degrees is or pi over 2 if we're in radians. What's the rest to make a right angle? In this diagram, we actually have the complementary angle. It's right there. So if we let phi be theta's complement, we've got another angle there, right? So if we look at that angle instead of the theta angle, we can ask all the same questions, just essentially horizontally instead of vertically. Our half chord, put it up here instead. So it's the half chord based on phi instead of based on theta. Make our tangent line come out horizontally instead of vertically. And look at our cut through length all the way out to that intersection instead. So this is still a sine length because it's still a half chord, but it's the sine length for our co-function. So it's the cosine. This is still a tangent length up here, but it's the tangent length for our co-function. So it's our cotangent. Similarly, that big, long red length, it's the cut through, it's the secant, but it's the secant for the co-function. Fair? So all those functions, the cotangent, the cosecant, and the sine, mean the same thing as sine, cosine, and tangent, just for the other angle, for the complementary angle, hence co, complement, co, or co-functions. So here's the fun part. Since all we've done is essentially switched ourselves from a vertical orientation to a horizontal orientation, all we've done is changed our y's and our x's. Fair? This red cosine value, it's not the y value anymore. What is it? Don't all shout at once. It's the x value. Fair? The tangent was the ratio between our y and our x. So it was our y to our x to give us that tangent. Well, it's the same argument up here. It's just that that cotangent is going to be x over y instead. Make the argument or horizontally instead of vertically. You can probably guess the cosecant. Instead of being 1 over the x, 1 over the y. So historically, and again, this is kind of the geometric and historical origins of these functions and their names and their orientations. And historically, the sine, tangent, and secant were thought of as the primary ones because those were the three that were based on that angle theta. Cosine was just it's the sine of the cofunction. But eventually, you'll notice the definition for cosine being just that x is so much handier than the 1 over x. Fair? And the secant and the cosine are just reciprocals of each other. So after a while, secant gets a little bit less favored, and we start preferring working with the cosine instead. Because if we know the cosine values, finding the secant values are easy. Fair? But in practical applications, you'll find sine, cosine, and tangent, they all come up a lot. But secant comes up fairly often. Of our secondary functions, that secant is pretty common, and that's because it has such a strong physical representation. Cosecant, you don't see come up a lot in practical applications, though it does. And cotangent, gosh, you almost never see cotangent come up in practical applications. It does happen, but it's not very common. All that seem reasonable so far? So these are our, let's kind of back up here, our unit circle definitions for our trigonometric functions. So if we have, oh, I got to make that. If we have a circle, right now we are stuck. We're going to undo it in a second, but a circle of radius 1, and we have a ray that intersects this circle anywhere. I'm going to put that ray here that intersects that circle. Even though this is now an angle too large to ever fit in a triangle, we can define our sine, cosine, tangent, cosecant, secant, and cotangent functions just by knowing that point of intersection. Let's say, for sake of argument, that point of intersection is negative, what do I want? How about negative 12/13? It's got to be negative because it's over in quadrant 2, so x has to be negative. And 5/13. Again, you can check to see if that is really on the circle of radius 1. I assure you it is. But if we know that point of intersection on the circle of radius 1, we know the sine value, the cosine value, the tangent, the secant, the cosecant, and the cotangent just by knowing that value. For example, what's the sine value?
Pi over 13.
Was that?
5/13.
What's the cosine value?
Negative 12/13.
Absolutely. Negative 12/13. What about the tangent value?
Five thirteenths over negative 12 thirteenths.
So you said 5/13 over negative 12/13, but of course you're going to reduce that, right? So how about negative 5/12? Cool. What about the cosecant? Cosecant was the reciprocal of
1/5/13.
yes, but you wouldn't leave it like that, would you? 1 over 5/13.
No.
You'd multiply by 13/5, or just flip it and get 13/5. That would make the secant equal to
Minus 13 over 12.
negative 13/12. Yep. And lastly, the cotangent.
Twelve over 5.
Ooh. Close.
Thirteen over 5.
Not as close.
Would it be negative 12 over 5?
Be negative 12/5. Yeah. So again, it's just our y value, our x value, our y over our x, which will often take some reducing. The reciprocal of our y value, the reciprocal of our x value, and the reciprocal of our tangent value. Now, notice being in quadrant 2 tells us our x values are going to be negative and our y values are going to be positive, right? So being in quadrant 2, we automatically know sine is going to be positive, cosine is going to be negative. Their ratio, a positive divided by a negative, is going to give us a negative. The cosecant is going to be positive because it's the reciprocal of something positive. The secant is going to be negative because it's the reciprocal of something negative. And the cotangent is going to be negative because it's the reciprocal of something negative. So just knowing what quadrant we're in, we know whether our functions are going to be positive or negative, which is kind of cool. Similarly, in quadrant 3, since everybody's negative in quadrant 3, both the x's and y's, the sine is going to be negative, the cosine is going to be negative. Tangent, though, negative divided by a negative, tangent's going to be positive down there. So cotangent's going to be positive, and secant and cosecant going to be negative. It's a nice implication of our definitions. Fair? Okay, but what if our circle doesn't have a radius of 1. All of this is based on that circle having a radius of 1. What if it doesn't? Oops. Well, just like these definitions are really just an extension of our triangular definitions, we should be able to adjust this for a radius, any radius, a radius r, without destroying what we've done. So let's say it was radius r, and let's say we have a point out here somewhere. Let's say it's the point -3, 4. And we want to figure out what the sine, cosine, tangent, cosecant, secant, and cotangent are for this angle with that point of intersection. Well, first and foremost, can we figure out what the radius is given that point -3, 4? So can we ask here, what is r? Yes, no, or maybe?
Yes, by the distance formula.
I'm going to argue, but I'm going to be very picky because I'm arguing. Less the distance formula and more the Pythagorean theorem. But that's because the distance formula is just a variation of the Pythagorean theorem. Fair? Distance formula and Pythagorean theorem have always been the same thing. So it really is the same argument. You could also have said by the definition, the equation of our circle, x squared plus y squared equals r squared. That's the equation of a circle centered at the origin of radius r. But that's also just Pythagorean theorem.
Right,
Right.
but the distance is the square root of r, and that's the distance formula I'm referring to.
Right. But that's still the square root of the change in x plus squared plus the change in y squared equals the distance. You square both sides of that, your Pythagorean theorem again. So they're all just versions of Pythagorean theorem. Fair? So you're certainly not wrong. I don't want to give you the impression I think you're wrong about that. It's just about a lot of our tools are going to be based around Pythagorean theorem. So thinking of it as that general tool is nice. But you're certainly not, I'm incorrect. So if we took that -3 squared plus 4 squared, tried to have that equal r squared, we'd have 9 plus 16 is r squared, so 25. And you're absolutely right. If we just square rooted it instead, we wouldn't have to deal with the whole plus or minus interpretation. But our radiuses are always considered positive, so our radius is 5. Is that orange hard to see on that black, or is it fine? Okay. How is the black, by the way? You guys cool with the black? For me, it's not as harsh, but I want to make sure you guys can see what I'm doing.
For me, it doesn't seem to make a difference versus the other way.
Oh, good. Okay, so if we wanted to figure out, we could kind of back up to this kind of diagram and kind of go through ratios and stuff again. But if we imagine, even if this circle is radius 5, could we put a circle of radius 1 inside that? And look at this point here. So that circle of radius 1, well, how does it compare to the circle of radius 5? Well, it's 1/5 the size, right? All we've done is scaled it down by 5. So if we wanted to find those coordinates, they would be the same as these coordinates, just scaled down by 5. Fair? instead of being just that y value, it would be that y value divided by that radius of 5 to scale it down. The cosine value would be x, but divided by that 5 to scale it down. Tangent, well, that radius didn't actually matter. The ratio between that x and that y is the same as the ratio between that x and that y because they're similar triangles. So that one doesn't even change. The reciprocals, okay, they change, but again, they're just scaled up by r, except for cotangent. So we could go through a similar triangle argument to prove that those are all the same, but it really is just a factor of scaling it. So given this intersection point, we can find the sine value 4 over r, so 4 over 5, or cosine -3 over 5, and so on. -4/3. 5/4, -5/3, and -3/4. So again, it's not really different than our unit circle definition. It's just kind of an extension of it. I'm going to go one further and say it's not even all that different from our triangular definition, because you can certainly see right here, there's a little right triangle, right? Didn't escape your notice, did it? Now the problem is this angle theta is not an interior angle of that triangle. The reason we can't just stick with opposites and adjacents and hypotenuse is because in terms of that angle theta, there is no adjacent hypotenuse opposite length because that theta is not an interior angle. But does that mean we can't think of this little triangle here and say, okay, that's kind of like an opposite, kind of like an adjacent, and kind of like a hypotenuse? As long as we're okay that that adjacent length is negative, well, how can adjacent lengths be negative in a triangle? It's not a real triangle, right? So as long as we allow ourselves to kind of pretend that that's a, a negative length in our triangle, these are still sort of opposites over hypotenuse and adjacent over hypotenuse, just in a triangle that doesn't really truly exist, but it's an extension of that triangular definition. So ideally, all the work you've put into so far about getting comfortable with those triangle definitions, they will carry over because the visualization is still there. It's just going to allow us to work in any angle of any size in any quadrant on a circle of any radius. We can still determine what these values are.
You say any radius. What about a radius of imaginary numbers?
It is possible, but it does get more complicated. We luckily will not be doing trig in the complex plane yet in your mathematical careers. Often you do that it's usually a 300 level math class for complex analysis, but you can define the trigonometric functions over complexly defined angles. It's just complexly defined angles are a weird concept. So you got to define what that means in terms of your system. But the definitions do extend a little bit strangely because you're dealing with them in a 4th dimensional space as opposed to a 2-dimensional space. So yeah, there's a lot to unpack if you try to use complex numbers in there, but it can be done. Okay. Questions about any of that so far? I know
I
you
just want
guys
to
have
let you
to.
know that your explanation was much clearer than the book, at least for me.
Well, I have the benefit of being able to take a certain amount of time and talk about some of this historical backing of where some of these things come from, you know. And I always kind of debate how much use is it of our time, you know, to go through these, you know, what do they mean physically? Where do they come from? Why are they called what they're called? That is a fairly time consuming argument, but I think it gives a little more context. So, and I got to be here for a reason, right? But what are you going to be asked to do based on this? Well, one of the first things, we certainly do have more to add to this subject. Oops, why did I put it over there? I don't know. There should be some way for me to move it. I just don't know how to do that yet. So let's say, you know, this goes through the point here, -7, 9. And you've got, and it doesn't have to be this angle. It could be that angle. You know, call that theta. Doesn't matter. If it's a negative, doesn't matter if it rotates around four or five times. As long as it's measured from standard position, that's our qualifier. As long as it's measured from standard position, we can find what is the tangent of that angle. Well, tangent is nice because all we need are the x's and y's. So how about -9/7? If somebody asked us what is the sine of that angle, well, the sine has to be y over r. So since this isn't a circle of radius 1, so the y value we know, but we'd have to go find r. Well, how do we find r?
Pythagorean theorem.
Pythagorean theorem. So what, 49 plus 81? That thing's square root is our radius, which, yes, makes it look a little bit more like a distance formula. It does put in a plus or minus, but again, our radius is going to be safe from that. So what is that, 130? So the square root of 130. So 9 over the square root of 130, which of course you would rationalize because you're polite people. I don't think the square root of 130 reduces, does it? Not a 4, it's not a 9, there's not a, yeah, I think that's solid. And that's a nice exact answer, so we leave it. That's the sine of that angle. Cool. Now, the next thing we have to talk about, we're talking about tomorrow, are our standard triangles and how they compare to our standard angles. You remember back middle of last week, we talked about those standard angles, the pi over 3, the pi over 4, and the pi over 6, corresponding to the 30 degrees, the 45 degrees, and the 60 degrees. I said the reason that those were our standard angles is because they have special geometric qualities. Why 30, 60, and 45 are special. They've got special geometry to them. And what we're going to talk about tomorrow is what that special geometry is. And knowing that special geometry is actually going to allow us to figure out what those coordinates are on not only our unit circle, but technically any size circle. So, you know, where does this intersect our circle of radius 1? We're going to find out tomorrow because of the special geometry of those 3 angles. All right. All right. Any questions before I let you guys go today?
Is that everything for 6-3 homework, or
No,
Do we
6-3
know?
homework is this, some of that too.
so should we start it or should we wait?
I'd start it.
Okay. Thank
Most
you.
of the first half of it is just kind of, this stuff. Given that point on some ray, find the sine, cosine, tangent, blah, blah, blah. So you can do that stuff, no problem. Anything else? All right. Well, have a wonderful day then. If something comes up that you need, let me know.
Thank you.
You're very welcome.